Okay. Okay. So the stuff that I'm going to tell you right now isn't really in the book, but it's important. So I'm going to call it secret mathematical knowledge. It's not secret, but it's useful and it's not in the book. So maybe in that sense it's secret. Okay. So we're going to start off with a lemma, which is actually, I think, part of your homework, but I'll give it to you anyway. I don't care. If T1 and T2 from V to W are linear transformations, that agree on a basis of V. Okay. That is, right, there's some basis, and on each element of the basis, they agree with each other. T1 of Bi equals T2 of Bi for every element. Okay. For every element of the basis. So suppose you have these linear transformations that agree on a basis of V, then they agree on every vector of V. So let me write up what I mean by the first part, just the first part. So you have let B, B1 to Bn be the basis of V on which T1 and T2 agree. In other words, T1 of Bi equals T2 of Bi for all I. Okay, and what we're hoping to show, we want to show, that for all V in V, T1 of V equals T2 of V. We want to see that these guys agree with each other. Yeah, Mia.
I'm sorry, what do you mean by agree?
Exactly this, that T1, if you take any element of the basis, then T1 of that element equals T2 of that element.
So the transformations are equivalent?
On the basis. So the only thing you know is that what they give agrees on the basis. So here you have some vector space, here you have some other vector space, right? You have T1 and T2. Okay. You have a basis of T1. Mm-hmm. You have a basis of V. Okay. And you look at what happens if you map each of these guys through T1. Okay. It turns out you get this, this, and this, say. Okay. And it turns out that T2 does exactly the same thing.
Oh,
okay. T2 does exactly the same thing. So T1 of V1 is T2 of V1. B1, sorry. B1. You have T1 of B2 is T2 of B2. You have T1 of B3 equals T2 of B3. Okay. So they agree on a basis. They do exactly the same things to a basis, and you're hoping to show that, in fact, they do the same thing to every vector. For every vector in the space, you get the same thing. They agree. So they're the same transformation. Okay.
So they're the same transformation.
That's right. That's right. So then they agree on every vector. In other words, T1 equals T2. Okay. If they agree on a basis, they agree everywhere. Okay, so I'll let you take a minute or two and see if you can see why this happens. We want to show that for any vector, they're going to agree with each other. This is actually straightforward. If you can do it in 2 minutes. Who are we missing? Are we missing somebody? No?
I don't know her name, but she always sits right over here.
Ah, Teresa, yeah. Okay, so how, right, so, like, let V, Teresa, right? We're also missing Zane, right? Zane, yeah. So let V be any guy in V, and we want to show that T1V equals T2V. Does anyone have an idea of how to do it? Would anyone like to venture a guess? Mia?
Is it because V is a linear combination of all the
We know that V is a linear combination of the V's. Right? So let's look at T1 of V. So T1 of V is going to be T1 of this combination. Right? And what do we know about T1 of a linear combination? A linear transformation of a linear combination? What can we do with it? Mia?
Distribute it.
Right. We can commute the addition. Right. This thing will pass through vector addition, and it will pass through the scalar multiplication. Right. So this, since T1 is a linear transformation, since T1 is linear, right, this is equal to summation I1, right, from 1 to n, C1 T1 Bi. Right? But we know that T1 Bi is the same thing as T2 Bi. Right? And then we go backwards, and we end up with T2 of V. Right? We commute, we pass T2 back out using its linearity. So we end up with T2, okay? Again, since T2 is linear, pass it back out, and we get T2 of summation Ci Bi. That's just from I equals 1 to n. Let's just say T2 of. So agreeing on the atoms that make up the space means that you agree on the whole space. Okay. Is that you, Teresa?
Yeah, it's telling me that I'm done.
You're done running?
Yeah.
Very good. Okay, any questions? Any questions? My brother uses the roar of Godzilla for his phone, like when it rings. It goes, I think that was maybe the first movie we watched when we were kids. Godzilla versus Megalon. I think the second movie was Star Wars.
Oh, that's a great one. Wait, four, right?
Yeah, the first one. Okay. Okay. Another notion, important one. T from V to W, a linear transformation. Is called one-to-one or injective. If whenever the outputs are equal, then the inputs must be equal. Okay. So you see what it says, like if t of v1 equals t of v2, it must be that v1 equals v2. Right? The only way that could happen is the only way you can get the same outputs is if you start with the same inputs. Okay. You can't have two different inputs going to the same output. Right? The only way you can get the same output is if the inputs are the same. Okay? Equivalently, if v1 is not equal to v2, then t of v1 is not equal to t of v2. Right? Different inputs go to different outputs. Okay? It's a one-to-one function. You never have two different inputs going to a single output. Right? That would be 2 to 1, or multiple to 1, many to 1. Okay, so 1 to 1 or injective. Claim t is 1 to 1. We often abbreviate this just 1-1. If and only if the kernel of t is what? What am I going to say? T is 1 to 1 if and only if the kernel is 0. Is the 0 vector. Okay, I think you might be able to just tell me why this happens. If t is 1 to 1, how do we know that the kernel is just the 0 vector? Mia.
I changed my mind. I don't want to say anything.
Okay. How do you know that the kernel of t is just the 0 vector? If t is 1 to 1, t is 1 to 1. Mia, go ahead.
Does it have to do with like t being unique?
T, I mean,
Never mind. I
t,
don't want.
okay. Okay.
Never mind.
Right. So t certainly, sends only one thing to the 0 vector. Right? T is being 1 to 1. T is 1 to 1, so we know it sends only one thing to the 0 vector. Right?
Oh, so then mostly, or like the kernel of t would have to be only 0
Yes.
because there couldn't be any other thing.
That's right. That's right. So right, exactly. So we know already that t of the 0 vector is 0. Right? Right. So the kernel of t contains the 0 vector. Okay. And we know that that's the only thing that gets sent to the 0 vector. Since t is 1 to 1, is the only element such that t of it is there. Only element that t sends to 0. Right? And so the kernel of t is exactly that. Okay, so that's pretty straightforward. The opposite direction is also not too hard.
What is,
Yeah, Emma. No, Mia.
what does it say after only?
The only element.
Oh, okay.
Sorry. Okay, the opposite direction. Suppose say that the kernel is the only thing sent. Suppose you know that the only thing sent to 0 is 0. How does that tell you that if you start off with two different guys, you're going to end up with two different guys. Or that if so you want to show if T of V1 equals T of V2, then V1 must equal to V2. Okay. This actually is also a not too difficult application of just linearity. Okay, so take a minute or two and see if you can figure it out. Okay, so why? So what do you think? If these guys are equal to each other, like TV1, suppose TV1 equals TV2. Okay. How are we going to get to V1 must equal to V2? We know that the kernel, the only thing that gets set to 0 is the 0 vector. Okay. The only thing that gets set to 0 is the 0 vector. TV1 equals TV2. And we know that this thing is a linear transformation. Right? Linear transformation. Anand.
I'm thinking what we said V1 is the 0 vector. And then
We don't know that. We don't know that. V1 and V2 are just some vectors. We want to show that for any vectors V1 and V2,
Oh,
that if TV1 equals TV2, then V1 equals V2. So we can't assume that they're the 0 vector. Itong.
Can you put the T of B2 to the left side? of the
Sure,
line?
right? That's, you know, we can certainly subtract, right? We can subtract, right? Because, you know, this is a vector, we're in a vector space, right? So, right, this is going to be 0. Right? Okay, so finish it off.
And T of V1 minus B2 equals
T of V1 minus V2 is the 0 vector. Right? In other words, V1 minus V2 is in the kernel of T. Right? But the kernel of T is 0. Right? V1 minus V2 is 0. Right? Which tells us that V1 equals V2. Okay, everyone all right with that? Any questions? Any questions? Okay. Okay. Another important definition. Again, we have a linear transformation. Is called onto. It's called onto if the image of V under T is all of W. I guess in the book's language, you say the range of T under V is W. What this means, practically speaking, is that given any W in W, there is a V in V such that TV equals W. Is it clear what onto means? It means that, you know, if you take anybody, you take any vector in the target space, there's some vector in the domain space that gets mapped onto it. Everybody can be realized as the image of somebody else, right? What about this guy? Oh yeah, there's some vector over here that gets mapped onto it. Right? What about this guy? Oh yeah, there's some vector over here that T maps onto it. Okay, so everything is hit. Everything in V is realizable as the image of something in V. To give you an example, V a vector space, V basis. Okay. So if you have, say, an n-dimensional vector space, and then you have some basis in it. Okay. You have some abstract vector space, and you have some basis in it. You remember we had this map. We have a map. V goes to V sub V. Right. You start off with a vector in V, and you map it to its coordinates with respect to the V basis. You remember this? I hope you remember this. Right. You take your vector, you express it as a linear combination of these guys, and you take those coefficients and you put them in a column, and you get this thing here. Okay. This map is onto. This is an onto map. Right. If I start off with any set of coordinates here, if I set off with any set of coordinates on our end, well, I can find some vector. I can make a vector back here that gets mapped to those coordinates. Right? I just use those coordinates to make a linear combination, and that's the thing that gets mapped to it. Right? Is that clear? That should be transparent, I hope. Right? If I start off with, somebody says, oh, what about 1, 2, 3, 4, 5? What about 1, 2, 3, 4, 5? Well, I'd say, okay, I'm going to come back here and go to B1 plus 2B2 plus 3B3 plus 4B4 plus 5B5, and call that V. And V, if I run it through this thing, this is the coordinate vector for that V. Right? So any coordinates you give me, I can find a vector that gets mapped onto that. Okay, so this is an onto map. Okay. Notice that this is also a one-to-one map, right? This is also a one-to-one map, right? Because if I end up with the same coordinates here, that means that I started off with the same vector back here. Right? So this map is actually an instance of both of these things. It's both one-to-one and onto. It's a special kind of map called an isomorphism. Okay. So if T a linear transformation is one-to-one and onto, I should say, since I gave the other definition, other term, people often use this this word instead of onto, surjective. If it's one-to-one and onto, then we call T an isomorphism. An isomorphism, and say V and W are isomorphic. Okay, so the symbol, one uses this symbol for isomorphism. V is isomorphic to W. Okay. So what this says over here, we could express this statement by saying that any n-dimensional vector space is isomorphic to Rn. Any n-dimensional vector space, right? Here we start off with a vector space. We take a basis and we get an isomorphism between it and Rn. So another way of saying this is that V is isomorphic to Rn. Or in fact, any n-dimensional vector space is isomorphic to Rn. Okay, any questions? It's a lot of language, but it's not complicated. Right, you have injectivity, right, one-to-oneness. You have onto, your surjectivity being onto, and you have both of those things. You have isomorphism. It's also called bijective, injective and surjective, bijective. Any questions? No, easy. Haley, you have questions? You're just kicking the floor. Why are you kicking the floor? You frustrated? It looks like frustration.
No.
Okay, it's not frustration. Okay. Okay. Different cultures have different expressions. What does this mean? If I do that, what does it mean to you?
Cute. Japanese cute.
No. It means you're angry for Japanese people.
Oh.
My wife is Japanese.
What else?
I feel like I've seen so many pictures.
Yeah.
She's being clueless.
What?
When I do that, it usually just means know what's going on.
Yeah, know what's going on.
Yeah. Ready to die.
Okay. Here's an exercise for you to try. So let A be an n by n matrix. Okay, so it's a square matrix, and T sub A, as usual, is going to be the map from Rn to Rn, given by given by T sub A B equals AB. Right? So it's the map given by left multiplication by the matrix. And here's the claim that T sub A is onto if and only if A is invertible. Okay, so remember you need to prove it both ways, right? That T is onto forces A to be invertible, A invertible forces T to be onto. The backwards this way is, I think, the easier way, and then the forwards direction is probably the trickier way. But it's not so bad. Okay, so take a few minutes and see if you can figure it out. T sub A is onto if and only if A is invertible. Sorry, I should ask, what part are you having trouble reading?
What does onto mean again?
Onto means that everything in the target space is covered by the image of T.
Oh, okay.
Okay, so like if you take anything in the target space, you can find some vector that gets mapped to that. Okay. Henry, I see like you're clueless.
Yeah. It's my natural state of mind. Oh, okay. So you need A over
No, I meant to. In this case, you know, A times
Okay, who would like to? Yes, Anand.
I actually have a question.
Yes.
So when you're defining an onto map, you're
Mhm.
basically saying that T is such that there is a vector in V which, when mapped using T, gives you a W.
Yeah. So
Right.
given any W in the target space, there's going to be somebody in the domain space that gets mapped to that thing.
Okay. Oh, okay.
Let me give you an example. So we looked at some map like this. Here's an xy, x comma 0, right? Here's a map, right? It turned out to be a linear transformation, right? It goes like this. It takes a vector and then projects it down onto the xy plane, onto the x-axis, right? So if this was xy, then it gets mapped to x comma 0, right? This map is not onto. This map is not onto, right? This is a map from R2 to R2, but it's not onto, right? Because there's nobody that gets sent to this guy, right? Who gets sent to this guy? 1, 1, nobody, right? All the outputs lie on the x-axis, so this is not an onto map. The rotation map, on the other hand, is an onto map, right? If you say T of xy, if your map is the one that says I take in a vector and then I rotate it by angle theta, rotate by some angle theta, right? Right? To give the resulting. So this is T of xy. Okay. Because then, if I say, well, what guy gets mapped to 1, 1? Well, I just I just take this 1, 1 and rotate it theta degrees this way, and I say, this guy gets mapped to 1, 1. right? This guy, because when I rotated theta degrees back, I get 1, 1. Right? So the rotation map was onto. Right? This projection map is not onto. Yeah, Teresa.
In this t of xy, is y the output of x? So
No.
you start with,
No.
or are they just two separate points?
Those are variables. Yeah.
Okay.
So x1, x2, if you like. x1,
Okay.
x2 gets mapped to x1, comma 0. Yeah. Okay, so let's try it. If A is invertible, then let's say that TA is onto. Anyone have an idea how to do it? Would anyone like to try it? Right? What do we want? Let's just think. What do we want to show? We want to show that if A is invertible, then given any vector in Rn, there's some other vector, maybe I'll call this one W, there's some vector V in Rn such that TAV is W. Right? We're looking for somebody gives us a target, and we can find something that hits that target. Okay? No matter what target we're given, there's a vector. We can find some vector that allows us to hit that target. Okay? So given W in Rn, what V do we choose? Right? What V do we choose? What V do we choose so that AV equals W? What V do we choose so that AV equals W? What's V? What must V be?
Can you just make it A inverse times W?
A inverse W, right? Let V be A inverse W. Okay, then TAV is A times A inverse W, which is W. Right? So if your matrix is invertible, then it's easy to hit anybody. Thus, T is on. Yeah, Mia.
What does it say below given any vector?
There's, sorry.
Oh.
There's some V in Rn such that we want to show that given any vector, there's some V that T sub A maps onto W. Okay. Now the opposite direction, I don't know if anybody made any headway. T sub A is onto. It says assume T sub A is onto. Right? That's to say that the collection of AVs, where V ranges through Rn, is all of Rn. Right? TAV, right? TAV is going to cover, as V ranges over your domain, you look at all the outputs, right? This is the collection of all outputs. All outputs cover the whole space, right? That's what onto means. Right? In other words, T of Rn, TA of Rn is Rn. In other words, if I look at TAV, that's all of Rn. In other words, if I look at this, that's all of Rn. I'm just writing the same thing over and over, 4 times now. Yeah, Ellen.
I'm not sure if
Go ahead,
this
go
will
ahead,
work,
yeah.
but if we assumed that A weren't invertible,
Oh, okay, sure.
then I could pick the target to be something that is invertible, and then A times that would be not invertible. So you couldn't get to anything in the target space that was invertible.
So if A is not invertible, then I'm not following what you say after that. So suppose-
Actually, never mind.
Okay.
Yeah.
Okay. Okay. But look at this, right? AV is all of Rn. AV, where V is in Rn, is all of Rn. Right? Maybe if I read it with a C, does it make it more suggestive? AC, C in Rn is all of Rn. What does that say about A? What does it say about A? We want to say something about A, that A is invertible. Right. Excuse my hunger.
Would you say that AC equals 0 vector has a unique solution?
Why? Why? I mean, it will turn out to be true, but why? What we know at this point is that A times, if we look at the matrix times C, and we let C range over all possible coefficients, and it turns out we get everything in Rn. Can anyone sort of rephrase this in terms of, say, column space? Katie? Not quite, not quite. So what is this? AC, as C ranges over all these things. This is the column space. This is the column space, right? As C range, the column space of A, right? Remember, right, these things are going to be C1, A1 plus C2, A2 plus C1, A1. Right? This is this, right? So what we're looking at here is actually the column space, right? So we write it again, i.e. the column space of A is all of Rn. Okay. Does that have anything to do with invertibility? The column space is all of Rn. In other words, the rank of A is n. The rank of A is n, and so the nullity, thank you. The nullity is 0. Right? And that tells you that by the rank theorem. Okay, so the nullity is 0, and that tells you that A is invertible. Okay, go ahead. Okay, is everyone all right? You seem kind of quiet today. Is it because Zane is not here? Without Zane, you guys have no power. Okay, so that's any questions on how this works? You say, oh look, assume TA is onto. TA is onto is the same thing as saying that the column space is all of Rn. Column space being all of Rn means that the nullity is 0, so you're invertible. Okay, so the main thing is to recognize the connection to the column space and then invoke the rank theorem.